Welcome, everyone. It's wonderful to have you here. Before we get started, would you let us know in the comments where you're tuning in from and the time of day it is for you? I love seeing how this space brings together people from across the globe. A heartfelt thank you as well to all who've subscribed and supported the channel. It helps me know what connects with you, and it helps others discover these calming moments too. And if inspiration strikes, please feel free to leave your ideas for future videos. With that said, let's begin. Chapter 1. Understanding Quantum Mechanics Foundations. Quantum mechanics, a realm where the familiar laws of classical physics dissolve into a curious dance of possibilities, invites us into a world that challenges our very understanding of reality. It is a framework that not only explains the behavior of the smallest particles in our universe, but also underpins the very fabric of the cosmos. This field is significant as it reveals the intricacies of matter and energy, shaping technologies that influence our everyday lives, from the smartphones we carry to the medical imaging devices that allow us to peer inside our bodies. To appreciate the significance of quantum mechanics, it is essential to journey through its historical development. The early 20th century marked a pivotal moment in scientific exploration, as physicists grappled with anomalies that classical theories could not explain. The classical view, rooted in determinism and predictability, began to unravel when experiments revealed that light could behave both as a wave and a particle. This duality was elegantly captured by Albert Einstein in his work on the photoelectric effect, where he suggested that light consists of discrete packets of energy called photons. As the quest for understanding continued, Niels Bohr proposed his model of the atom, introducing the idea that electrons inhabit specific energy levels and can transition between them, emitting or absorbing energy in the process. This marked a significant shift from classical notions of orbiting planets to a more abstract representation of atomic structure. With these foundational ideas, physicists began to realize that the microscopic world operates under principles that defy our intuitive grasp of reality. The historical tapestry of quantum mechanics is woven with the contributions of remarkable thinkers. Werner Heisenberg, with his uncertainty principle, posited that certain pairs of properties, like position and momentum, cannot both be precisely known at the same time. This revelation hinted at the inherent limitations of measurement and observation in the quantum realm. Imagine a universe where knowledge is not absolute, but probabilistic, where the act of observing affects the very nature of what is observed. As we delve into the core principles of quantum mechanics, three concepts stand out: superposition, entanglement, and uncertainty. Superposition describes the ability of a quantum system to exist in multiple states simultaneously. Picture a spinning coin suspended in time, embodying both heads and tails until it lands. This principle is not merely a philosophical musing. It has practical implications in technologies such as quantum computing, where bits can represent both 0 and 1 at the same time, exponentially increasing computational power. Entanglement, another cornerstone of quantum mechanics, reveals a profound interconnectedness between particles. When two particles become entangled, the state of one instantaneously influences the state of the other, regardless of the distance separating them. This phenomenon, famously described by Einstein as spooky action at a distance, challenges our classical intuitions about locality and separateness. Imagine a pair of gloves tossed into different corners of the universe, yet knowing the state of one instantly reveals the state of the other, no matter how far apart they are. Uncertainty, as articulated by Heisenberg, introduces a fundamental limit to our knowledge of certain properties of particles. It beckons us to reconsider the nature of reality itself. If we cannot simultaneously know both the position and momentum of a particle, what does that say about the predictability of the universe? This uncertainty is not just a limitation of our measurement tools. It is woven into the very fabric of existence. It invites us to embrace a new narrative, one where outcomes are probabilistic rather than deterministic. Mathematics serves as the language of quantum mechanics, providing the structure through which these abstract concepts are expressed and understood. The equations that describe quantum phenomena are often non-intuitive, requiring a shift in our thinking. The wave function, a mathematical representation of a quantum state, encapsulates all the possible outcomes of a measurement, revealing the probabilities of finding a particle in various states. Through the language of mathematics, we are granted access to a deeper understanding of the underlying principles that govern the behavior of particles. Renowned physicist Richard Feynman once remarked, "The only thing that counts is the probability of the various outcomes." This encapsulates the essence of quantum mechanics, where the future is not predetermined, but a realm of potentials waiting to be realized. The mathematics of quantum mechanics allows us to navigate this landscape of probabilities, transforming the abstract into the tangible. Consider the elegance of the Schrödinger Equation, a fundamental equation that describes how the quantum state of a physical system changes over time. It is through this equation that we can predict the behavior of particles, from electrons within an atom to photons traversing the cosmos. Each term in the equation carries significance, illustrating the relationship between energy, time, and the wave function. As we immerse ourselves in the world of quantum mechanics, we find ourselves at the intersection of science and philosophy. The implications of these principles extend beyond the laboratory, prompting us to question our understanding of reality itself. What does it mean to exist in a world governed by uncertainty? How does entanglement challenge our notions of separateness? These questions invite us to ponder not only the nature of the universe, but also our place within it. The journey through quantum mechanics is not merely an academic pursuit. It is an exploration of the mysteries that define our existence. As we contemplate the significance of these foundational concepts, we begin to appreciate the beauty that lies in the unknown. It is an invitation to embrace curiosity, to seek understanding where answers may be elusive, and to celebrate the marvels of a universe that is, at its core, an intricate mosaic of probabilities and possibilities. In this exploration, we stand on the shoulders of giants, drawing inspiration from the brilliant minds that have shaped our understanding of the quantum realm. Each discovery, each equation, adds a brushstroke to a magnificent canvas that represents our quest for knowledge. As we continue this journey, we will uncover the layers of quantum mechanics, revealing the profound truths that lie beneath the surface, waiting to be discovered. In the intricate web of quantum mechanics, the role of mathematics cannot be overstated. It serves as both a tool and a lens through which we examine the universe at its most fundamental level. The mathematical framework of quantum mechanics is steeped in abstraction, often requiring a rethinking of how we approach scientific inquiry. Consider the concept of the wave function, a central element in quantum theory that encapsulates all the information about a quantum system. Imagine the wave function as a symphony, with every note representing a possible state of the system. Just as a symphony can evoke a multitude of emotions and interpretations, the wave function holds within it the potential for countless outcomes. When we observe a quantum system, we essentially collapse this symphony into a single note, a specific state that we can measure and understand. This process, while mathematically defined, is deeply philosophical, urging us to confront the nature of reality itself. The beauty of mathematics in quantum mechanics lies in its ability to describe phenomena that defy everyday experiences. For instance, the probabilistic nature of quantum events invites us to reconsider how we define certainty and knowledge. The famous double-slit experiment exemplifies this beautifully. When particles such as electrons are fired at a barrier with two slits, they create an interference pattern that suggests they behave as waves, passing through both slits simultaneously. Yet when we attempt to measure which slit a particle goes through, the interference pattern vanishes, revealing a singular path. This paradox challenges our understanding of causality and observation. How can a simple act of measurement alter the very behavior of a particle? This question has intrigued physicists and philosophers alike, prompting a myriad of interpretations within the quantum community. The Copenhagen interpretation, popularized by Niels Bohr and Werner Heisenberg, posits that physical systems do not have definite properties until they are measured. In contrast, the many worlds interpretation, proposed by Hugh Everett, suggests that all possible outcomes of quantum measurements are realized in branching, parallel universes. This divergence in interpretation highlights the richness of quantum mechanics, where the mathematical formalism may lead to different philosophical implications. As we ponder such interpretations, we are invited to embrace the ambiguity that comes with the quantum realm. It compels us to ask, what does it mean to observe? What is the relationship between the observer and the observed? In the realm of applied quantum mechanics, the mathematical principles extend their reach into a myriad of technologies. Quantum computing, as previously mentioned, harnesses superposition and entanglement to process information in ways that classical computers cannot. Imagine a future where problems deemed unsolvable due to their complexity could be tackled with unprecedented speed. This potential is not confined to theoretical musings. It is rapidly becoming a reality, with companies and research institutions racing to develop practical quantum systems. The journey into quantum mechanics also brings us face to face with the concept of quantum tunneling. This phenomenon occurs when a particle passes through a potential energy barrier that it classically should not be able to surmount. Picture a ball rolling up a hill. Classically, it must have enough energy to reach the top, otherwise it rolls back down. However, in the quantum world, the ball might inexplicably appear on the other side of the hill, having tunneled through the barrier. This principle underpins processes such as nuclear fusion, which fuels stars and consequently the very existence of life on Earth. As we explore these principles, we come to appreciate the contributions of visionary scientists like Max Planck, whose introduction of quantized energy levels laid the groundwork for the field. Planck's insights were initially met with resistance, yet they paved the way for a revolution in physics. Science cannot solve the ultimate mystery of nature, he once stated. And that is because, in the last analysis, we ourselves are a part of the mystery that we are trying to solve. His words resonate profoundly within the quantum realm, reminding us that inquiry is as much about the questions we ask as it is about the answers we seek. Throughout this journey, we cannot overlook the significance of experimental validation in quantum mechanics. The interplay between theory and experiment is a hallmark of the scientific method, but in quantum mechanics, it takes on an extraordinary dimension. The act of measurement itself becomes a crucial component of the theory, creating a unique feedback loop where observation influences the outcome. This aspect invites us to reflect on the role of the observer in shaping reality. Are we merely passive witnesses, or do we actively participate in the unfolding of events? As we continue to unravel the complexities of quantum mechanics, we find ourselves immersed in a realm of profound implications. Each principle, from superposition to entanglement, beckons us to reconsider the nature of existence, knowledge, and the universe itself. The mathematical elegance that describes these phenomena serves as a reminder of the interconnectedness of all things, inviting us to marvel at the intricate web of reality. The exploration of quantum mechanics is not merely a scientific endeavor. It is an invitation to embrace the unknown. It encourages us to confront our assumptions, challenge our perceptions, and venture into the depths of mystery. As we delve further into this captivating world, we are reminded that at the heart of quantum mechanics lies a celebration of curiosity, an acknowledgement of the beauty in uncertainty, and a reverence for the wonders that await discovery. Thus the adventure continues, revealing layers of understanding that deepen our appreciation of the universe. Each discovery acts as a stepping stone, urging us to question, to wonder, and to explore the profound truths that quantum mechanics unveils. What other mysteries lie hidden within the quantum realm, waiting for the next generation of thinkers to uncover? The journey is far from over, and the quest for knowledge beckons us forward into the vast expanse of possibility. Chapter 2. Defining wave functions in quantum mechanics. In the realm of quantum mechanics, the notion of a wave function emerges as a cornerstone, a bridge connecting the abstract world of quantum particles to the tangible reality we experience. At its essence, a wave function is a mathematical description that encapsulates the state of a quantum system. It serves as a powerful tool, enabling us to understand and predict the behavior of particles at the quantum level. Imagine a wave function as a complex, multidimensional entity that provides insight into the probability of finding a particle in a given location. It is often symbolized by the Greek letter psi, representing a wave-like phenomenon that embodies the dual nature of particles. This duality, highlighted in earlier discussions, posits that particles can behave both as discrete entities and as waves, oscillating through space, their positions and momenta intertwined in a delicate balance of uncertainty. Mathematically, wave functions are expressed through complex valued functions. These functions may take different forms depending on the specific quantum system under study. For instance, in one-dimensional systems, wave functions can be represented as a function of position, often denoted as SI of x, where x signifies the position along a line. In three-dimensional space, the wave function expands to include additional dimensions, reflecting the intricate dance of particles within their environments. One of the key properties of wave functions lies in their normalization. This concept ensures that the total probability of finding a particle within a specified region of space equals 1. In practical terms, this means that if we were to integrate the probability density derived from the wave function over all possible positions, it would yield a complete certainty that the particle exists somewhere in that space. This necessity for normalization grounds wave functions in reality, allowing them to serve as reliable descriptors of quantum states. Continuity is another essential characteristic of wave functions. As we contemplate the quantum world, we find that a well-defined wave function must vary smoothly across space. Abrupt changes in the wave function would imply an infinite probability density, which is not physically plausible. This continuous nature reinforces the notion that particles do not exist in discrete jumps, but instead exhibit a fluid presence across their quantum landscape. The importance of wave functions transcends mere mathematical formalism. They are vital in defining quantum states, acting as the foundation upon which the entirety of quantum mechanics is built. Each quantum state, represented by a unique wave function, conveys information about the particle's properties, such as its energy, momentum, and position. Consider how, for instance, the wave function of an electron in an atom reveals the intricate structure of its orbitals, defining regions of space where the electron is most likely to be found. This probabilistic interpretation underscores the inherent uncertainty that permeates the quantum realm. Renowned physicist Max Born famously stated, "The wave function is a complete description of the system." This assertion encapsulates the pivotal role wave functions play in quantum mechanics, offering a lens through which we can observe and predict interactions at the subatomic level. As we explore the implications of wave functions, we begin to appreciate how they facilitate our understanding of phenomena that defy classical intuition. Imagine yourself observing an electron. Instead of pinpointing its exact location, we contemplate a cloud of probabilities, a visual representation of the wave function. This cloud, often referred to as an electron cloud, illustrates the various locations where the electron might be found, revealing the inherent uncertainty that characterizes its existence. The shape and density of this cloud shift based on the energy state of the electron, providing a dynamic view of its behavior. As we delve deeper into wave functions, we encounter the intriguing concept of superposition. In quantum mechanics, particles can exist in multiple states simultaneously, a phenomenon that defies our classical understanding. The wave function captures this essence, allowing for a combination of probabilities that manifests as a superposition of states. This principle is beautifully illustrated in the thought experiment known as Schrödinger's cat, where a cat exists in a state of being both alive and dead until observed. The wave function embodies the probabilities of these states, reinforcing the idea that reality is not as straightforward as it seems. Moreover, wave functions are not static. They evolve over time, governed by the Schrödinger equation, which serves as the fundamental equation of motion in quantum mechanics. This equation describes how the wave function changes, allowing us to predict the future behavior of quantum systems based on their initial states. The evolution of wave functions introduces a sense of dynamism to the quantum world, where particles dance through possibilities, their trajectories shaped by the underlying mathematical framework. As we reflect on the significance of wave functions, it becomes evident that they are not merely mathematical abstractions. They are essential tools that empower scientists to unlock the mysteries of the quantum universe. Through wave functions, we can model complex systems, explore interactions between particles, and predict the outcomes of experiments that challenge our understanding of reality. Consider the implications of wave functions in the development of technology. Quantum mechanics has led to groundbreaking innovations, such as quantum computing and quantum cryptography, which rely on the principles of superposition and entanglement. The wave function is at the heart of these advancements, guiding researchers as they explore new frontiers in computation and communication. As we navigate through the intricate world of quantum mechanics, the wave function stands as a testament to the beauty of mathematical elegance intertwined with the mysteries of existence. It invites us to ponder profound questions about the nature of reality itself. What does it mean for a particle to exist in multiple states? How do wave functions shape the interactions between particles? These questions echo through the annals of scientific inquiry, inviting us to explore the depths of our understanding. In the whispers of quantum theory, where the familiar dissolves into the enigmatic, the wave function serves as both a guide and a puzzle. It beckons us to embrace uncertainty and to find comfort in the dance of probabilities that defines the quantum realm. As we continue our journey through this captivating landscape, let us carry with us the knowledge that wave functions are not just abstract concepts, but fundamental elements that illuminate the path toward a deeper understanding of the universe. As we immerse ourselves further into the intricacies of wave functions, we encounter an essential characteristic, the concept of superposition. This remarkable principle allows quantum systems to exist simultaneously in multiple states, a phenomenon that defies our classical intuitions. Picture a serene lake, its surface undisturbed, yet beneath, currents swirl and intertwine, each representing a different potential state of a quantum particle. The wave function captures this amalgamation of possibilities, offering a glimpse into a realm where the traditional boundaries of existence blur. The superposition of states is crucial to understanding phenomena, such as quantum interference and entanglement. Imagine two particles, each described by its own wave function. When these particles interact, their wave functions overlap, leading to a new, combined wave function that embodies the probabilities of both particles. This interaction creates a rich tapestry of outcomes, illustrating how the very essence of quantum systems is interwoven and interconnected. The historical context of this concept reveals the contributions of eminent physicists who dared to challenge established norms. Erwin Schrödinger, a key figure in quantum mechanics, introduced the wave equation that bears his name. His innovative thinking led to the formulation of the wave function, which not only describes a system's state, but also evolves over time. In his own words, Schrödinger expressed the depth of this idea when he stated, "I do not like it, and I cannot accept it." This sentiment captures the struggle many physicists faced as they grappled with the implications of the quantum world. As we explore the mathematical representation of wave functions, we find ourselves navigating through complex valued functions. These functions are more than mere equations. They encapsulate the probabilities of finding a particle in various states. When we visualize the wave function, it is reminiscent of a symphony, with each note representing a different aspect of the quantum state. This harmony of probabilities allows scientists to predict outcomes, even in the face of uncertainty. Normalization is pivotal in this mathematical framework. ensuring that the total probability of finding a particle sums to 1. This principle is akin to a delicate balance in nature, where all possibilities must coexist harmoniously. If we were to disregard normalization, we would encounter paradoxes, such as an infinite probability density, which would render our understanding of quantum mechanics untenable. The requirement for normalization thus reinforces the reality that wave functions are grounded in the physical world, bridging the gap between abstract mathematics and tangible existence. Beyond normalization, continuity serves as another cornerstone in the behavior of wave functions. Consider a calm river flowing gently along its banks. Abrupt changes in the flow would be jarring, disrupting the tranquility of the landscape. Similarly, a wave function must exhibit continuous variation across space, ensuring that the probabilities it conveys do not leap unreasonably from one value to another. This smooth transition reflects the underlying nature of particles, which do not simply appear and disappear, but rather exist in a fluid continuum. The importance of wave functions extends far beyond their mathematical properties, acting as the bedrock of quantum states. Each unique wave function not only defines a particle's state, but also encapsulates vital information about its energy and momentum. As we contemplate the structure of an atom, the wave functions of its electrons reveal intricate orbitals that dictate their probable locations. Imagine stepping into an ethereal garden, where the petals of each flower correspond to different electron states, each one a testament to the wave function's descriptive power. The advancements in technology inspired by wave functions are profound. Quantum mechanics has given rise to innovations that transform our lives, from lasers to magnetic resonance imaging. These technologies leverage the principles of wave functions, using the probabilistic nature of quantum states to create devices that enhance our understanding of the world and improve our daily experiences. With each technological leap, we witness the tangible impact of quantum mechanics, reminding us that the mysteries of the subatomic realm are not confined to theoretical musings. As we reflect on the significance of wave functions, we are drawn to the philosophical implications they carry. What does it mean for reality when particles can exist in multiple states? What does it reveal about the nature of observation and measurement? These questions linger, inviting us to ponder the very essence of existence itself. The wave function serves as a lens through which we can explore these profound queries, encouraging us to embrace the uncertainties that lie at the heart of the quantum world. In the fabric of quantum mechanics, wave functions act as both a guide and a mirror, reflecting our quest for understanding. They challenge us to reconsider the nature of reality, pushing the boundaries of our comprehension. As we move forward in our exploration of quantum mechanics, let us carry with us the realization that wave functions are not merely tools for calculation, but rather gateways to the mysteries of the universe. Through them, we are invited to question, to dream, and to explore the infinite possibilities that lie within the quantum realm. Chapter 3. Interpreting Wave Functions Physically. In the intricate world of quantum mechanics, the connection between wave functions and probability is as profound as it is essential. As we continue our exploration, we find that wave functions do not merely represent the state of a quantum system. They embody the probabilities of various outcomes, painting a vivid picture of possibilities rather than certainties. Imagine standing on the edge of a vast ocean, where each wave represents a potential reality, each crest and trough signifying a different outcome awaiting our observation. The Born interpretation provides a crucial framework for understanding this connection. According to Max Born, the wave function square, represented as psi squared, translates to a probability density. This means that the wave function does not tell us where a particle is located, but rather how likely it is to be found in different positions. Picture a foggy landscape where the density of fog corresponds to how probable it is to encounter a hidden treasure. The denser the fog, the more likely you are to stumble upon that treasure. In quantum mechanics, the areas where the wave function's probability density is high indicate where a particle is more likely to be detected during a measurement. When we measure a quantum system, something remarkable occurs. The wave function undergoes a transformation known as collapse. Prior to measurement, the particle exists in a superposition of states, where it embodies all possible locations or states simultaneously. Imagine a dreamy state where possibilities float like clouds, each one equally viable. Yet when we observe or measure the particle, it instantaneously collapses into one of those possibilities, as if a spotlight suddenly illuminates a single cloud, making it the focus of our reality. This phenomenon raises intriguing questions about the nature of reality itself and what it means to observe in the quantum realm. Consider the implications of wave function collapse on our understanding of determinism. In classical mechanics, the universe operates like an intricate clock, with each tick and tock predictable based on initial conditions. However, quantum mechanics introduces an element of unpredictability that challenges this deterministic view. If the act of observation can alter the outcome, can we truly claim that the universe is deterministic? This notion echoes the thoughts of physicist Eugene Wigner, who reflected on the role of consciousness in quantum mechanics, suggesting that it is not just the measurement itself, but the observer's awareness that plays a pivotal role in the unfolding of reality. As we ponder these ideas, we might ask ourselves, what does it mean to be an observer in this context? Are we merely passive witnesses, or do we play an active role in shaping the realities around us? The answers remain elusive, yet the discussions they inspire are vital to our understanding of the universe. The very act of observation becomes a bridge between the probabilities described by wave functions and the tangible reality we experience. The implications of these concepts extend beyond abstract thought, influencing fields ranging from quantum computing to the philosophical underpinnings of reality. In quantum computing, for instance, the principles of superposition and entanglement are harnessed to perform calculations that would be impossible with classical bits. Here, wave functions become the language of computation, where qubits exist simultaneously in multiple states, akin to a symphony of possibilities harmonizing to create a unique outcome. As we continue to explore the fascinating landscape of quantum mechanics, we encounter remarkable individuals who have contributed to our understanding of wave functions. One such figure is Richard Feynman, who famously remarked that the behavior of quantum particles is not merely strange, but also beautifully intricate. His insights into the nature of quantum electrodynamics have illuminated the dance of particles and waves, revealing the elegance of the universe at its most fundamental level. Feynman invited us to embrace the strangeness of quantum mechanics, recognizing it as a natural part of the cosmic order. In the realm of quantum mechanics, the wave function serves as a beacon, guiding us through the vast sea of probabilities. It challenges us to reconsider our assumptions about reality, inviting us to explore the depths of uncertainty and the interplay of observation and existence. The more we uncover, the more we realize that at the heart of quantum mechanics lies a profound mystery, a tapestry woven from threads of chance, observation, and the very essence of what it means to be. As we delve further into this captivating journey, the question lingers: how do we reconcile the probabilistic nature of quantum mechanics with our desire for certainty? Is the universe, at its core, a realm of pure potential, where every moment is a crucible of possibilities waiting to be forged into reality? The exploration of wave functions and their implications reveals more than just the behaviors of particles. It beckons us to reflect on the nature of existence itself. The interplay between wave functions and probability invites us to ponder the delicate balance between chaos and order, chance and choice, as we venture deeper into the mysteries of the quantum world. As we reflect on these concepts, we might also consider the role of our own consciousness in this unfolding narrative. How does our awareness shape the probabilities presented by wave functions? This question leads us into a realm where science and philosophy intertwine as we seek to understand not only the mechanics of the universe, but also our place within it. The exploration of wave functions is not merely an academic pursuit, it is an invitation to engage with the very fabric of reality. With each layer we unravel, we move closer to understanding the nature of existence, the dance of particles, and the significance of observation. As we continue this journey, let us remain open to the possibilities, embracing the uncertainties that lie ahead, while appreciating the beauty of the quantum world around us. Each insight gained serves to deepen our connection with the universe, reminding us that we are part of something far greater than ourselves, a cosmic symphony that transcends the boundaries of time and space. As we continue to explore the implications of wave function collapse, we encounter the profound notion that reality is not merely a static backdrop, but rather a dynamic interplay of possibilities brought to life through observation. This interplay suggests that the universe may be less about deterministic pathways and more about a web of potentialities, interwoven with the fabric of consciousness itself. Consider the act of measurement in quantum mechanics. When we engage in this act, we do not simply uncover a hidden truth. Instead, we invoke a transformation that collapses the wave function, selecting a particular outcome from a myriad of possibilities. This transformative process invites us to ponder what truly constitutes an observation. Does it require the presence of a conscious observer, or can it occur through any interaction with the environment? The debate continues, with some scientists positing that any measurable interaction, no matter how mundane, can trigger collapse, while others insist that consciousness plays an irreplaceable role. This distinction leads us to the work of physicist John von Neumann, who articulated a framework for understanding measurement in quantum mechanics. He proposed that the observer's consciousness is integral to the measurement process, suggesting a deeper connection between mind and matter. Imagine standing before a vast canvas, where each brushstroke represents a potential reality, and your perception brings forth a vivid image. In this metaphor, your consciousness acts as the artist, shaping the final outcome from the spectrum of possibilities. The implications of wave function collapse extend into the very heart of determinism in the universe. In classical mechanics, the universe is often envisioned as a well-oiled machine, predictable and orderly, where the results of every action can be foreseen based on initial conditions. However, quantum mechanics disrupts this comforting paradigm, introducing an element of fundamental unpredictability. The idea that observation can alter the course of events raises an essential question. Is the universe inherently deterministic, or does it embrace a degree of randomness? This philosophical inquiry has captivated the minds of many, including physicist Niels Bohr, who argued that quantum mechanics challenges our classical intuitions. He famously stated, "We are not only not able to measure the reality of a situation, but we have to understand that the reality is created by our observation." This perspective compels us to reconsider our assumptions about the nature of reality itself. Could it be that our engagement with the universe shapes it in ways we have yet to fully comprehend? As we ponder these questions, we may find ourselves reflecting on the implications for our understanding of free will. If the act of observation plays a pivotal role in determining outcomes, how does this influence our beliefs about choice and agency? Are we mere spectators in a preordained universe, or do we possess the power to influence the unfolding tapestry of existence? These reflections resonate deeply within the philosophical discourse surrounding quantum mechanics, blurring the lines between science, consciousness, and free will. In navigating the landscape of these profound ideas, we also encounter the work of physicist David Bohm, who offered an alternative interpretation of quantum mechanics, known as the pilot wave theory. This perspective suggests that particles are guided by a deterministic wave function, implying a hidden layer of reality that operates beneath the apparent randomness observed in experiments. Bohm's insights challenge us to consider the possibility that the universe may harbor deeper truths that remain concealed from our immediate perception, inviting further exploration and contemplation. As we embrace the implications of wave functions and their relationship with probability, we are reminded of the interconnectedness of all things. Each measurement, each act of observation, reverberates through the cosmos, weaving a complex narrative that transcends the boundaries of time and space. Picture a grand orchestra where every note played contributes to a symphony of existence, each wave function a musical phrase that resonates with the universe. Our role as observers is to listen, to engage, and to participate in this cosmic performance. In the world of quantum computing, the interplay of wave functions takes on new significance. These remarkable systems harness the principles of superposition and entanglement, allowing qubits to exist in multiple states simultaneously. The potential for quantum computers to perform calculations at unimaginable speeds relies on this very relationship, where the wave function serves as a guiding force, orchestrating the outcome of complex computations. Imagine a realm where the impossible becomes possible, where the fabric of reality is transformed into a canvas for innovation and discovery. As we delve deeper into the quantum realm, we encounter the profound realization that the study of wave functions is not merely an intellectual exercise. It is a journey that invites us to explore the very essence of existence. Each revelation beckons us to reflect on our own role within the universe, urging us to embrace the uncertainties and marvel at the intricate dance of particles and waves. In this exploration, we may ask ourselves, what lies beyond our current understanding? What mysteries await discovery as we continue to peel back the layers of reality? The pursuit of knowledge in quantum mechanics is akin to wandering through an ethereal garden, where each blossom represents a new insight, a fresh perspective, waiting to be uncovered. As we draw upon the wisdom of those who have come before us, we find inspiration in the words of physicist Albert Einstein, who expressed that the most beautiful experience we can have is the mysterious. This sentiment encapsulates the essence of our journey through quantum mechanics, a journey that embraces the unknown and finds beauty in the questions that arise. With each step we take, we inch closer to understanding the delicate interplay of wave functions, probability, and observation, recognizing that our exploration is part of a greater narrative that spans the cosmos. As we continue this odyssey, let us remain open to the wonders that lie ahead, ready to engage with the mysteries of the universe and our place within it. The journey is far from complete, and the unfolding story of quantum mechanics invites us to delve deeper, exploring the profound connections that bind us to the very fabric of existence. Chapter 4. Solving the Schrödinger Equation. The Schrödinger equation stands as a pillar in the landscape of quantum mechanics, a mathematical formulation that elucidates how quantum systems evolve over time. At its core, this equation captures the essence of quantum behavior, allowing us to predict the future state of a system based on its current wave function. Imagine it as a guiding map through the intricate web of possibilities that define the quantum realm, where the familiar certainties of classical physics give way to a more fluid understanding of reality. When we speak of the Schrödinger equation, we encounter two distinct forms, the time-dependent and the time-independent equations. The time-dependent Schrödinger equation governs the evolution of a quantum state over time, encapsulating the dynamic nature of particles as they interact with their surroundings. In contrast, the time-independent form emerges in scenarios where the energy of the system remains constant, suitable for systems in stationary states. This separation offers clarity, allowing us to focus on specific aspects of quantum behavior while still embracing the full complexity of the universe. Consider the time-dependent Schrödinger equation, which can be expressed as a function of both space and time. It reveals how the wave function changes, responding to the influences of potential energy within a given space. This equation serves as a foundation for understanding phenomena such as tunneling, where particles appear to pass through energy barriers that classical physics would deem insurmountable. Imagine a tiny particle, like an electron, seemingly vanishing from one side of a barrier and reappearing on the other, as if it had slipped through a secret door. This behavior, counterintuitive as it may seem, is beautifully described by the time-dependent equation. On the other hand, the time-independent Schrödinger equation allows us to explore systems in a more static context. It simplifies the investigation of a system's energy levels, revealing quantized states that particles can occupy. In this form, the equation sheds light on the allowed energy levels of an electron within an atom, illustrating how it can only exist in specific states. This is akin to imagining a staircase, where each step represents a distinct energy level, and the electron can only rest on these steps, never in between. The quantization of energy levels is a hallmark of quantum mechanics, challenging our classical intuitions and leading to profound implications in fields ranging from chemistry to material science. The applications of the Schrödinger equation are numerous, extending beyond mere academic curiosity into the practical realms of technology and medicine. For instance, it plays a crucial role in the development of semiconductors, the backbone of modern electronics. By understanding how electrons behave within these materials, scientists can engineer devices that power our smartphones and computers. Additionally, the Schrödinger equation provides insight into the behavior of molecules, enabling chemists to predict how substances will react, influencing everything from drug design to the development of new materials. To grasp the power of the Schrödinger equation, let us consider a simple yet illustrative example: the particle in a box. This thought experiment encapsulates the fundamental principles of quantum mechanics in a clear and approachable manner. Picture a particle confined within an infinitely deep box, unable to escape. The walls of this box represent an impenetrable barrier, and the particle's wave function must adhere to specific conditions. Namely, it must be zero at the walls. As we solve the time-independent Schrödinger equation for this system, we discover that the particle can only occupy certain quantized energy levels. The solutions reveal wave functions that resemble standing waves, with nodes where the probability of finding the particle is zero. This phenomenon is akin to the vibrations of a plucked string, where only specific frequencies produce stable oscillations. Each energy level corresponds to a different wave function, with the lowest energy state, or ground state, being the most stable configuration. Imagine observing this particle as it oscillates within the confines of its box. The wave function tells us where it is most likely to be found, painting a vivid picture of its probabilistic nature. The areas where the wave function is dense indicate a higher likelihood of detecting the particle, while the nodes signify regions of impossibility. This fundamental insight into the behavior of particles not only enriches our understanding of quantum systems, but also lays the groundwork for more complex scenarios involving multiple particles and interactions. The beauty of the Schrödinger equation lies not only in its ability to describe isolated systems, but also in its adaptability to a plethora of quantum scenarios. From atoms to molecules to condensed matter systems, its principles resonate throughout the fabric of the quantum world. Scientists have harnessed its power to design quantum computers, where qubits leverage the principles of superposition and entanglement, pushing the boundaries of computation into realms previously thought unattainable. The legacy of the Schrödinger equation is also reflected in the words of its namesake, Erwin Schrödinger, who once remarked, "The wave function does not represent reality, it is reality." This profound statement underscores the equation's significance in reshaping our understanding of existence itself. It invites us to consider not just the mathematical solutions, but the very nature of reality as described by quantum mechanics. As we continue to explore the depths of the Schrödinger equation, we find that it serves as a vital tool for unlocking the mysteries of the universe. The interplay between time-dependent and time-independent forms allows us to appreciate the dynamic and static aspects of quantum systems, each offering a unique perspective on the behavior of particles. In this intricate dance of mathematics and physics, the Schrödinger equation stands resolute, revealing the hidden patterns beneath the surface of reality. Each solution, whether for a simple particle in a box or a complex molecular system, contributes to our broader understanding of the quantum world. Imagine standing on the threshold of a vast ocean of knowledge, where each wave of discovery beckons you to dive deeper into the mysteries of existence. The Schrödinger equation is your guide, illuminating the path through the intricate landscape of quantum mechanics. As we continue our journey, we will encounter more complex systems, unveiling the rich tapestry of interactions that define our universe. As we delve further into the applications of the Schrödinger equation, we encounter an array of fascinating quantum systems that illustrate its profound implications. One of the most compelling aspects of this equation is its ability to describe not just isolated particles, but also systems of multiple particles, leading us into the rich domain of quantum mechanics, where entanglement and superposition reign supreme. Imagine a pair of entangled particles, connected in such a way that the state of one instantaneously influences the state of the other, regardless of the distance separating them. This phenomenon, often referred to as spooky action at a distance, challenges our traditional notions of locality and causality. The Schrödinger equation provides the mathematical framework to describe these intricate relationships, allowing us to calculate the probabilities of various outcomes when measurements are made on entangled systems. The implications of entanglement stretch far beyond theoretical musings. They have practical applications in the burgeoning field of quantum computing. In this new frontier, quantum bits, or qubits, leverage the principles of superposition and entanglement to process information in ways that classical bits cannot. Picture a qubit existing in a state of both 0 and 1 simultaneously, enabling parallel computation that could revolutionize problem-solving in fields ranging from cryptography to materials science. The contributions of scientists like David Deutsch, a pioneer of quantum computing, reflect the potential of harnessing the Schrödinger equation for practical advancements. Deutsch famously stated, "We are all made of quantum particles. If we can understand the behavior of these particles better, we can unlock new technologies that will shape our future." This insight captures the essence of how the Schrödinger equation not only explains the behavior of particles, but also serves as a gateway to transforming our technological landscape. In addition to entangled systems, the Schrödinger equation's versatility allows it to describe phenomena in various domains, from quantum optics to condensed matter physics. Consider the behavior of electrons in a solid material, where their interactions give rise to complex properties such as conductivity and magnetism. The time-independent Schrödinger equation shines in this context, revealing the energy band structure of materials. Imagine a crystal lattice, where atoms are arranged in a repeating pattern, forming a beautiful geometric structure. The electrons inhabiting this lattice behave according to the rules laid out by the Schrödinger equation, leading to the formation of valence and conduction bands. These bands dictate whether a material acts as an insulator, a conductor, or a semiconductor. This understanding has profound implications for the design of electronic devices, enabling the creation of everything from transistors to solar cells, which are pivotal in our modern technological landscape. As we explore more examples of solving the Schrödinger equation, it becomes clear that simplicity often yields profound insights. The infinite potential well, or particle in a box, serves as a foundational model, but the same principles extend to more complex systems, such as the hydrogen atom. In the case of the hydrogen atom, the Schrödinger equation reveals the allowed energy levels of the electron as it orbits the nucleus. The solutions to this equation yield wave functions that describe the electron's probability distribution in three-dimensional space. Imagine the familiar shapes of atomic orbitals, with their intricate patterns illustrating where an electron is likely to be found. The spherical symmetry of the s orbital contrasts sharply with the more complex shapes of the p and d orbitals, highlighting the diversity of quantum states available to the electron. This exploration of atomic structure not only enriches our understanding of matter, but also lays the groundwork for advances in chemistry and materials science. By predicting the behavior of electrons in atoms, chemists can better understand chemical bonding and molecular interactions, paving the way for innovations in pharmaceuticals and materials engineering. As we reflect on the myriad applications of the Schrödinger equation, it becomes evident that its reach extends into several fields, intersecting with our daily lives in ways we often take for granted. The very technologies that power our devices, the medicines that heal us, and the materials that shape our world are intertwined with the principles established by this elegant equation. In contemplating these applications, one might wonder how the Schrödinger equation continues to inspire new discoveries. One answer lies in the ongoing research in quantum mechanics, where scientists are constantly pushing the boundaries of what we understand about the universe. The advent of quantum technologies, including quantum sensing and quantum cryptography, showcases the evolving significance of the Schrödinger equation. Imagine a future where quantum sensors can detect gravitational waves or measure magnetic fields with unprecedented precision. Such advancements could revolutionize fields such as geology, medicine, and fundamental physics, allowing us to explore the cosmos and the very fabric of spacetime in ways previously deemed impossible. In this context, the Schrödinger equation emerges not merely as a mathematical tool but as a beacon, guiding us through the uncharted territories of quantum exploration. Each solution it offers reveals not only the behavior of particles, but also the potential for technological revolutions that can reshape our world. As we continue our journey through the landscapes of quantum mechanics, we find ourselves at the intersection of theory and innovation. The Schrödinger equation, with its dual forms and applications across various systems, remains a testament to the beauty and complexity of the quantum realm. Embracing this complexity, we open ourselves to the wonders that await as we delve deeper into the mysteries of the universe. Chapter 5. Wave functions in different quantum systems. In the realm of quantum mechanics, we encounter a fascinating distinction between free particles and bound states. Free particles, unencumbered by forces, exist in a state of perpetual freedom, their wave functions extending infinitely through space, embodying a range of possible positions and momenta. Imagine these particles as travelers in an open field, able to roam freely, their paths dictated by their inherent energies. The wave functions of free particles typically represent plane waves, smooth and unconfined, which can be expressed mathematically as sine or cosine functions. These waves spread out like ripples in a pond, indicating that a free particle can be found anywhere, with a uniform probability across space. Bound states, on the other hand, present a different narrative. Here, particles are confined within a potential well, their energies restricted, and their wave functions shaped by the forces that bind them. Picture a child playing in a cozy room filled with soft toys. The walls of the room define the boundaries of play, just as the potential well confines the particle. The wave functions of bound states exhibit distinct features. They are localized, exhibiting peaks where the probability of finding the particle is highest, while tapering off to zero at the edges of the potential well. This localization reflects the energy quantization inherent in bound systems, where only specific energy levels are permissible. One of the quintessential examples of a bound state in quantum mechanics is the harmonic oscillator. The harmonic oscillator model, often used to describe systems in physics, captures the essence of oscillatory motion. Imagine a child on a swing, moving back and forth in a rhythmic pattern. The wave functions of a quantum harmonic oscillator take on a unique shape, characterized by a series of distinct energy levels. These wave functions resemble a series of peaks and valleys, aligned like a set of neatly arranged hills, with the lowest energy state corresponding to the ground state, where the particle is most likely to be found near the center of the potential well. The higher energy states create additional nodes, points where the probability density drops to zero, reflecting the oscillatory nature of the system. The harmonic oscillator also reveals the beauty of quantization. Each energy level is spaced apart by a constant amount, allowing us to express the energy of a state using a simple formula. This elegant arrangement showcases how the deterministic world of classical mechanics gives way to the probabilistic landscape of quantum mechanics. As physicist Richard Feynman once remarked, "The only way to understand quantum mechanics is to study it." Through this lens, we can appreciate how the wave functions of harmonic oscillators not only describe the behavior of individual particles, but also underpin the vibrations of atoms and solids, and the arrangement of molecules in complex systems. Transitioning from oscillators, we arrive at the hydrogen atom, which serves as a cornerstone in our understanding of atomic structure. The wave functions in hydrogen models reveal the intricate dance between an electron and its nucleus, governed by the attractive force of electromagnetic interaction. Imagine the electron as a celestial body, orbiting around a sun-like nucleus, yet instead of fixed paths, it is surrounded by a cloud of probabilities. The wave functions of the hydrogen atom take on a spherical symmetry, visualized as electron clouds that fill the space around the nucleus. These clouds illustrate the likelihood of finding the electron at various distances from the nucleus, forming distinct shapes known as atomic orbitals. Each orbital corresponds to a specific energy level, with the lowest energy state represented by the ground state, a spherical cloud closest to the nucleus. As we ascend to higher energy levels, the orbitals become more complex, branching into shapes reminiscent of dumbbells or even more intricate forms. This complexity reflects the quantized nature of energy levels in the atom, a concept that Albert Einstein highlighted when he stated, "The most incomprehensible thing about the world is that it is comprehensible." The wave functions of hydrogen not only illustrate the structure of the atom, but also provide insights into the behavior of atoms in chemical reactions, where interactions between different electron configurations shape the material world around us. As we explore further, we encounter the phenomenon of quantum tunneling, a striking implication of wave functions that challenges our classical intuitions. Imagine a ball at the base of a hill, unable to roll over the top due to insufficient energy. In classical mechanics, the ball remains trapped, unable to traverse the barrier. However, in the quantum realm, the wave function does not adhere to such limitations. Instead, it can extend beyond the barrier, allowing for the possibility that the particle may tunnel through to the other side, even if it seemingly lacks the necessary energy. This concept transforms our understanding of what is possible, illustrating how limitations perceived in the classical world dissolve in the quantum landscape. Quantum tunneling plays a pivotal role in various natural processes. It is fundamental to nuclear fusion, the process that powers stars, including our sun. In the core of the sun, hydrogen nuclei must collide with enough energy to overcome their mutual repulsion. However, due to quantum tunneling, even particles with insufficient energy can occasionally tunnel through the barrier, leading to fusion reactions that release immense energy. This remarkable phenomenon exemplifies the interconnectedness of quantum mechanics and the cosmos, revealing how the tiniest particles can drive the grandest processes in the universe. Furthermore, quantum tunneling is not limited to astrophysics. It has profound implications in fields such as chemistry and electronics. It enables enzymatic reactions in biological systems, where molecules must navigate energy barriers to achieve transformation. This tunneling effect facilitates complex biochemical processes, illustrating how quantum mechanics subtly weaves its way into the fabric of life itself. As we reflect on these concepts, we are reminded of the profound implications of wave functions across different quantum systems. From the free particles that dance through the vastness of space to the bound states that reveal the structure of atoms, each wave function embodies a unique story, a narrative shaped by the underlying principles of quantum mechanics. The harmonic oscillator, the hydrogen atom, and the phenomenon of quantum tunneling all serve as reminders of the beauty and complexity that characterize the quantum realm. Each wave function draws us deeper into the mysteries of existence, inviting us to explore and appreciate the intricate dance of particles that defines our universe. As we delve into the properties of wave functions in harmonic oscillators, we notice that these wave functions offer a rich landscape of energy quantization. Each energy level corresponds to a unique wave function, revealing how particles behave in a potential well-defined by a restoring force. This model is not only foundational in quantum mechanics but also provides insight into various physical systems, from molecular vibrations to the behavior of atoms and solids. Imagine a series of ornate staircases, each step representing a distinct energy level. The particle, bound by the potential well, can only rest on these steps, never in between. This quantization leads to the emergence of discrete energy levels, which can be visualized as a ladder, a structure that illustrates the limitations and possibilities inherent in quantum mechanics. The ground state, the lowest step, represents the most stable configuration of the particle, where it possesses the least energy. As we move to higher energy states, the wave functions become increasingly complex, transforming into a symphony of oscillatory patterns. The shapes of these wave functions can be pictured as standing waves, which emerge as the particle oscillates within the confines of the well. These standing waves are characterized by nodes, points where the probability of finding the particle is zero, interspersed with antinodes, where the likelihood is at its peak. This delicate balance of probability reveals how quantum particles exist in a state of constant motion, even at their lowest energy state. The harmonic oscillator not only illustrates fundamental quantum principles but also serves as a vital tool in understanding more complex systems, such as phonons in solids and the behavior of electrons in atoms. Transitioning to the hydrogen atom, we find a magnificent example of how wave functions illuminate the structure and behavior of atoms. The wave functions of the hydrogen atom, derived from solving the Schrödinger equation, exhibit a spherical symmetry that reflects the attractive force between the electron and the nucleus. Imagine the nucleus as a radiant sun, with the electron as a planet orbiting in a cloud of probabilities. The shapes of these orbitals are not merely artistic. They represent the regions in space where an electron is likely to be found. The simplest orbital, the s orbital, resembles a smooth, spherical shell enveloping the nucleus. As we progress to p orbitals, we encounter shapes that resemble dumbbells, with the electron's probability density distributed across two lobes. These orbitals serve as the foundational building blocks for chemical bonding, illustrating how the arrangement of electrons determines the properties of matter. The intricate dance of these electrons, governed by their wave functions, underpins the vast array of chemical interactions that shape our material existence. A crucial aspect of the hydrogen atom lies in its energy levels, which are quantized and inversely proportional to the square of the principal quantum number. This relationship illustrates how electrons can occupy only specific energy states, a concept that fundamentally alters our understanding of atomic structure. The transition of an electron from one energy level to another, often accompanied by the emission or absorption of a photon, is a vivid demonstration of the interplay between energy and quantum states. As we consider these transitions, we recognize the profound impact they have on phenomena such as spectroscopy, where the emission and absorption spectra of elements reveal their unique identities. Delving deeper into the implications of wave functions, we arrive at the phenomenon of quantum tunneling, which challenges our classical intuitions in remarkable ways. Picture a ball rolling toward a hill. In classical physics, if the ball lacks sufficient energy, it will roll back, never reaching the other side. However, in the quantum realm, the ball's wave function can extend beyond the hill, suggesting a surprising possibility, tunneling through the barrier. This notion evokes a sense of wonder, prompting us to consider the limitations of our classical understanding. Quantum tunneling is not merely an abstract concept. It has tangible implications across various fields. In nuclear physics, it plays a pivotal role in enabling fusion reactions within stars. Amid the incredible temperatures and pressures at a star's core, hydrogen nuclei can occasionally tunnel through the energy barrier separating them, resulting in the fusion that powers the sun. This process serves as a reminder of how quantum mechanics governs the very fabric of the universe, influencing the birth and evolution of celestial bodies. Moreover, tunneling extends its reach into the realm of chemistry. Enzymatic reactions, which facilitate the biochemical processes essential for life, often rely on tunneling to overcome energy barriers. When molecules interact, they may need to transition from one state to another, a challenge that quantum tunneling deftly navigates. This phenomenon illustrates the interconnectedness of quantum mechanics and biology, revealing how the complexities of life are underpinned by the principles that govern the smallest particles. As we reflect on the profound implications of wave functions across different quantum systems, we are reminded of the intricate relationships that bind the universe together. From the bound states of harmonic oscillators to the elegant structure of the hydrogen atom, each wave function tells a unique story, an exploration of probabilities, interactions, and the underlying principles of existence. Perhaps we can contemplate the beauty of these systems, envisioning how the wave functions serve as both a map and a guide through the quantum landscape, illuminating the paths taken by particles as they traverse the vast expanse of possibility. In this dance of probabilities, we find not only a deeper understanding of the universe, but also a reflection of our own quest for knowledge and connection within the cosmic tapestry. Chapter 6. Visualizing wave functions, graphs, and models. Visualizing wave functions in quantum mechanics opens a window into the otherwise unseen world of particles and their behaviors. The complexities of these phenomena can be challenging to grasp, but through various visualization techniques, we can cultivate a deeper understanding. Imagine standing before an artist's canvas, where mathematics and artistry converge to depict the ethereal nature of quantum reality. Each brushstroke represents an aspect of a wave function, guiding our minds through a realm that defies conventional perception. One of the primary techniques for visualizing wave functions involves graphical representations of probability distributions. These distributions illustrate where a particle is likely to be found upon measurement, depicted as a series of peaks and valleys on a graph. Visualizing these distributions helps us to appreciate the probabilistic nature of quantum mechanics. Picture a landscape where hills symbolize high probabilities and valleys signify regions of low probability. In one-dimensional space, a wave function may appear as a series of oscillating curves, reflecting the probability density across various positions. The peaks of these curves indicate locations where a particle is more likely to be detected, while the troughs suggest areas where detection is less likely. This graphical representation mirrors the delicate interplay of certainty and uncertainty that lies at the heart of quantum mechanics. Extending this visualization to three-dimensional systems, we encounter more complex shapes, often resembling intricate patterns akin to delicate lace or rippling water. These three-dimensional surfaces, known as probability clouds, give us a tangible sense of where a particle might reside in space. Envision a wispy cloud enveloping a point, growing denser in areas where the likelihood of finding the particle increases. In the quantum world, these visualizations are not merely artistic representations. They embody the mathematical descriptions of wave functions, allowing us to grasp the abstract concepts that govern quantum behavior. As Richard Feynman once remarked, "If you think you understand quantum mechanics, you don't understand quantum mechanics." This highlights the necessity of visualization, as it offers a bridge between the complex mathematics and our intuitive understanding of the physical world. Wave function animations take this concept a step further, illustrating the dynamic nature of quantum behavior. These animations bring the wave functions to life, showcasing how they evolve over time. Imagine a wave undulating gently on the surface of a tranquil lake. As time progresses, the waves interact, merge, and change shape, reflecting the underlying quantum processes. Such animations allow us to witness the dance of probabilities, where particles exist in superpositions, oscillating between different states until measured. Consider the famous double-slit experiment, a cornerstone of quantum mechanics. In this experiment, particles are fired towards a barrier with two slits, and as they pass through, they create an interference pattern. This pattern cannot be explained by classical physics, but is beautifully illustrated through animations of wave functions. Picture each particle behaving like a wave, spreading out and overlapping as it travels through both slits simultaneously. The resulting interference pattern emerges as a vivid display of probabilities, revealing the fundamental nature of quantum superposition. The role of visualization in understanding quantum concepts extends beyond mere representation. It shapes our comprehension of the underlying principles. When we visualize wave functions, we become more attuned to the subtleties of quantum behavior. These visual tools help demystify the abstract notions of uncertainty and probability, allowing us to explore the strange and wondrous world of quantum mechanics in a more relatable manner. To illustrate this importance, let's delve into the pioneering work of physicists like Erwin Schrödinger, who introduced the wave equation that describes how wave functions evolve over time. By visualizing his mathematical formulations, we can appreciate the profound implications of wave behavior. Schrödinger's wave equation allows us to predict how a particle's wave function changes, illuminating the quantum landscape. Visualizations also play a crucial role in communicating complex ideas to a broader audience. They enable educators and scientists to convey intricate concepts in a manner that transcends traditional teaching methods. Imagine a classroom filled with eager minds, witnessing the unfolding of quantum phenomena through captivating visuals. This engagement sparks curiosity and fosters a deeper appreciation for the mysteries of quantum mechanics. The digital age has brought forth an array of sophisticated software tools that enhance our ability to visualize wave functions. These tools allow researchers and students alike to manipulate parameters, observing how changes in energy levels or potential wells affect the shape of probability distributions. Such interactive experiences empower learners to explore the quantum realm at their own pace, unraveling its intricacies in an engaging manner. As we continue our exploration of wave functions, we may ponder, how does visualization influence our intuition regarding quantum mechanics? The answer lies in the way these representations ground abstract concepts in visual experiences. When we can see the ebb and flow of probabilities, we become more adept at grasping the fundamental tenets of quantum behavior. Moreover, visualizing wave functions fosters a sense of wonder and curiosity about the universe. It encourages us to ask questions that challenge our understanding of reality. What if our perception of time is not linear? What if particles are not as isolated as we believe, but rather part of a vast interconnected web of possibilities? These reflections invite us to delve deeper into the mysteries of existence, fostering a sense of humility in the face of the universe's complexity. In the spirit of exploration, we can also examine the visualization of phenomena, such as quantum entanglement. This intriguing concept describes how particles can become intertwined, sharing states instantaneously, regardless of distance. Visualizing this interconnectedness can evoke images of a cosmic web, where distant particles communicate across vast expanses of space, defying our classical notions of separation. It invites us to reimagine our understanding of space and time, challenging the very foundation of how we perceive the universe. As we visualize these entangled states, we can begin to appreciate the profound implications of quantum mechanics on our understanding of reality. In the grand tapestry of quantum mechanics, visualizing wave functions serves as a key that unlocks the door to deeper comprehension. It bridges the divide between the abstract and the tangible, transforming complex mathematical concepts into vivid imagery that resonates with our intuitive understanding. Through these visualizations, we embark on a journey that not only enriches our knowledge, but also awakens a sense of awe at the beauty of the quantum world. As we reflect on these visual techniques, it becomes evident that they are not merely tools for representation, but are essential for fostering a deeper understanding of the quantum realm. They guide us through the complexities of wave functions, probability distributions, and the behavior of particles, illuminating the path toward a more profound grasp of the universe's mysteries. The beauty of quantum mechanics lies not only in its mathematical elegance, but also in its capacity to inspire curiosity and wonder. With each visualization, we take a step closer to unveiling the profound truths that lie at the heart of reality, inviting us to contemplate our place in this intricate and ever-unfolding cosmos. Visualizing wave functions also compels us to confront intriguing phenomena that arise in multi-particle systems. When we consider systems with multiple particles, the complexity of wave functions increases significantly. These wave functions can no longer be visualized as simple curves or clouds. Instead, they become intricate constructs that encapsulate the interactions and correlations between particles. Imagine a symphony, where each instrument contributes to a harmonious whole, creating a rich auditory experience. In a similar way, the wave function of a multi-particle system reflects the combined probabilities and interactions, forming a high-dimensional landscape that mirrors the complexity of quantum relationships. One of the most captivating aspects of multi-particle systems is the emergence of entangled states. When particles become entangled, their wave functions intertwine in such a way that the state of one particle is fundamentally linked to the state of another, no matter the distance separating them. This phenomenon can be visualized through the metaphor of a pair of dancers, moving in tandem regardless of the space between them. Their movements are synchronized, revealing a profound connection that transcends physical separation. The visual representation of entangled states often takes the form of a network or a web, where nodes represent particles and the connections illustrate their entangled states. This visualization serves as a powerful reminder of the non-locality inherent in quantum mechanics, challenging our classical intuitions about distance and interaction. How can two particles, light years apart, instantaneously affect one another? This question invites us to reevaluate our understanding of causality and connection in the universe. The implications of entanglement extend far beyond mere visualization. They resonate through the realms of quantum computing and cryptography. In the quest for powerful computational technologies, researchers are exploring how entangled particles can be harnessed to perform calculations at unprecedented speeds. Picture a future where quantum computers, utilizing the principles of entanglement, solve complex problems in mere moments, illuminating pathways to discoveries previously thought unreachable. Furthermore, the visualization of wave functions aids in understanding concepts like quantum tunneling. This phenomenon occurs when particles traverse potential barriers that they would not be able to surmount according to classical physics. Visualizing this process can evoke images of waves surging against a cliff, where certain portions of the wave manage to penetrate the barrier, revealing the probability of finding the particle on the other side. This visualization not only illuminates the counterintuitive nature of quantum behavior, but also showcases the delicate balance of probabilities that govern these transitions. As we delve into the representation of quantum tunneling, we may also consider the role of potential wells in shaping particle behavior. Visualizing a potential well can be akin to imagining a deep valley, where the particle's wave function is confined, creating standing waves that reflect the allowed energy states. Picture a pebble dropped into a bowl. It settles into the lowest point, representing the most probable energy state. This analogy extends to the concept of quantization, where only certain discrete energy levels are permissible within the confines of the well. In many ways, the visualization of wave functions serves as a gateway to understanding these complex phenomena. It allows us to create mental models that transcend mathematical abstraction, fostering a sense of connection to the underlying principles of quantum mechanics. As we engage with these visualizations, we may find ourselves contemplating the nature of reality itself. What does it mean for a particle to exist in multiple states simultaneously? How do we reconcile the probabilistic nature of quantum mechanics with our daily experiences of certainty? Throughout the history of physics, many great minds have grappled with these questions. Albert Einstein, known for his skepticism of quantum mechanics, famously remarked, "God does not play dice with the universe." His insistence on a deterministic framework reflects a profound desire to comprehend the deeper truths of nature. Yet, the visualizations we explore reveal a universe that is more akin to a flowing river, where probabilities ebb and flow, shaping the reality we perceive. In this light, visualization becomes a tool not only for understanding but also for appreciating the inherent beauty of quantum mechanics. It cultivates a sense of wonder, inviting us to engage with the mysteries of the universe. Imagine standing beneath a starlit sky, contemplating the vastness of existence. Each star twinkles with the potential of countless stories, much like the wave functions that encapsulate the myriad possibilities of particles. As we progress through our journey of visualizing wave functions, we become more attuned to the nuances of quantum behavior, the interplay of waves and particles, the intricacies of entanglement, and the phenomena of tunneling all converge in a kaleidoscopic display of reality. This journey encourages us to embrace uncertainty and to seek understanding in the face of complexity. Ultimately, the visualization of wave functions not only enriches our grasp of quantum mechanics, but also nurtures our curiosity about the universe. It beckons us to question, to explore, and to marvel at the delicate fabric of reality that unfolds before us. Each visualization becomes a stepping stone, guiding us further into the enigmatic realm of quantum phenomena, where the boundaries of knowledge continue to expand, inviting us to partake in the adventure of discovery. Chapter 7. Quantum Superposition and Entanglement Explained. In the realm of quantum mechanics, the concept of superposition invites us to embrace a reality that defies our everyday intuition. Imagine a world where particles exist not in a singular state, but in a blend of possibilities, each coexisting in a delicate balance. This phenomenon is known as superposition, where a quantum system can be in multiple states at once until it is observed or measured. Picture a spinning coin suspended in midair, representing both heads and tails simultaneously. It is only when the coin lands that it adopts a definite outcome, but until then, it embodies the essence of superposition, a vivid example of how quantum entities behave. Superposition is significant because it underpins many of the unique characteristics of quantum systems. It allows particles to exist in a multitude of states, which can lead to intricate outcomes when they interact with one another, or when they are observed. This principle not only challenges classical notions of reality, but also forms the foundation for quantum computing and information theory. As physicist Richard Feynman once remarked, "Nature isn't classical, dear reader. It is quantum mechanical." This idea propels us into a deeper understanding of how the universe operates at its most fundamental level. Now let's explore entangled states, another captivating aspect of quantum mechanics. When particles become entangled, their properties become interconnected, regardless of the distance separating them. This means that the state of one particle instantaneously influences the state of another, even if they are light years apart. Imagine two distant stars, twinkling in the night sky, yet their fates are intertwined, sharing a bond that transcends the vast emptiness of space. Entanglement challenges our conventional understanding of locality and separability. Albert Einstein famously referred to this phenomenon as spooky action at a distance, expressing his skepticism regarding the implications of entangled states. Yet, experimental confirmations have consistently demonstrated the reality of entanglement, revealing a profound interconnectedness among particles that reshapes our perception of the universe. The remarkable properties of entangled states have led to fascinating experimental demonstrations. One of the most famous experiments is the Bell test experiments, which have been conducted in various forms. These tests aim to verify the predictions of quantum mechanics against local hidden variable theories, which assert that particles have predetermined properties before measurement. The results of these experiments have overwhelmingly supported the quantum mechanical predictions, consistently showing violations of Bell's inequalities. Imagine a world where measurements on one entangled particle can influence another, leading to correlations that cannot be explained by classical physics. This realization prompts us to reconsider the very fabric of reality itself. As we reflect upon these concepts, we find ourselves at the intersection of quantum mechanics and technology. The implications of superposition and entanglement have sparked a revolution in quantum computing and information theory. Unlike classical bits, which exist as either 0 or 1, quantum bits or qubits can exist in a superposition of both states. This capability allows quantum computers to process vast amounts of information simultaneously, opening pathways to solving problems that are currently intractable for classical computers. Imagine a powerful machine that can explore multiple solutions at once, navigating through a labyrinth of possibilities with an elegance that surpasses our best efforts. Furthermore, the power of entanglement enhances quantum communication protocols, enabling secure information transmission through quantum key distribution. This innovative approach utilizes the principles of quantum mechanics to create encryption methods that are theoretically impervious to eavesdropping. Picture two individuals sharing a secret message through a series of entangled particles, their communication shielded by the very laws of nature. As we delve further into the experimental landscape, we encounter notable figures who have significantly advanced our understanding of these concepts. One such figure is Alain Aspect, whose groundbreaking experiments in the early 80s demonstrated strong evidence for the reality of quantum entanglement. His work not only validated theoretical predictions, but also paved the way for future explorations in quantum mechanics. Aspect's experiments illuminate the intricate dance of particles, revealing the delicate interplay of superposition and entanglement that weaves through the quantum world. The journey through quantum mechanics is not merely academic, it is a profound exploration of our understanding of reality itself. The principles of superposition and entanglement compel us to reconsider the boundaries of our knowledge, inviting us to engage with a universe that is far more interconnected and intricate than we could have ever imagined. As we ponder the implications of these concepts, we may ask ourselves, how does this knowledge reshape our view of the universe? The answers may lie in the ongoing quest for understanding, as scientists and researchers continue to uncover the mysteries of quantum mechanics, illuminating the path toward a future where the potential of these principles can be fully realized. Imagine a world where quantum computers harness the power of superposition to solve complex problems in seconds, offering solutions to challenges in fields such as medicine, materials, science, and cryptography. This is not a distant dream but a burgeoning reality, as researchers tirelessly work to translate these abstract concepts into tangible advancements. As we stand on the brink of this quantum revolution, we may find ourselves filled with anticipation for what lies ahead, eager to witness the transformation brought forth by the marriage of superposition and entanglement. As we continue our exploration of quantum mechanics, we recognize that the principles of superposition and entanglement are not merely theoretical curiosities. They are gateways to understanding the universe and unlocking its hidden potential. With each revelation, we inch closer to a comprehensive grasp of the quantum realm, revealing layers of complexity that challenge our perceptions and expand our horizons. The journey through this enigmatic landscape unfolds before us, inviting us to embrace the marvels of quantum mechanics and the wonders they promise for our future. The intricate world of quantum mechanics reveals layers of understanding that extend far beyond our classical perspectives. As we explore the experimental demonstrations of superposition and entanglement, we encounter a rich tapestry of discoveries that illuminate these concepts. Picture a serene laboratory, where the air is charged with anticipation and scientists are poised at the edge of a breakthrough. These experimental setups are not merely tests, they are gateways to unveiling the mysteries that govern the quantum realm. One of the pivotal experiments illustrating superposition is the double-slit experiment, a classic demonstration that continues to captivate minds. Imagine a beam of light or a stream of electrons directed toward a barrier with two slits. When both slits are open, a wondrous interference pattern emerges on a screen behind the barrier, suggesting that each particle has passed through both slits simultaneously, creating a wave-like behavior. This elegant pattern of light and dark bands reveals the essence of superposition, as each particle exists in a state of possibility until it is measured. The act of observation collapses this delicate wave function, forcing the particle to choose a definitive path and resulting in a single, localized outcome. As we ponder this experiment, we might ask ourselves, What does it mean for reality when observation alters the state of a system? This question invites us into the philosophical depths of quantum mechanics, where the boundaries between observer and observed blur, challenging our understanding of causality and existence. Turning our attention to entanglement, we encounter another extraordinary demonstration that has reshaped our understanding of quantum correlations. The phenomenon known as quantum teleportation serves as a profound illustration of entangled states in action. Envision two entangled particles, separated by vast distances, yet still intimately connected. When one particle is manipulated, say its spin is altered, the other particle instantaneously reflects this change, regardless of the space that lies between them. This phenomenon not only reinforces the notion of entanglement, but also raises questions about the nature of information transfer in the quantum realm. Research conducted by notable physicists such as Anton Zeilinger has propelled the field of quantum information forward. Zeilinger's experiments have demonstrated the feasibility of quantum teleportation and its implications for quantum communication. Imagine a future where information can be transmitted instantaneously through entangled particles, offering insights into a new era of secure communication channels. Zeilinger's work exemplifies the potential of harnessing the mysteries of quantum mechanics to transform our technological landscape. As we reflect on the experimental landscape, we must consider the significant implications of superposition and entanglement for quantum computing and information theory. The unique properties of qubits, which can represent both 0 and 1 simultaneously due to superposition, allow quantum computers to perform calculations in ways that classical computers cannot. Visualize a quantum computer as an orchestra, each qubit playing its part in a complex symphony of calculations, working in harmony to solve problems that would take classical machines years to unravel. Furthermore, quantum entanglement enhances the capabilities of quantum computing by enabling parallel processing. Imagine a vast library of books, each representing a different solution to a problem. A quantum computer can explore many of these books at once, sifting through information in ways that classical computers, bound by linear processing, cannot match. This powerful advantage opens the door to solving complex challenges in fields ranging from cryptography to drug discovery, where the exponential speed-up offered by quantum computations can lead to breakthroughs previously thought unattainable. The intersection of quantum mechanics and technology is not merely theoretical. It is a thriving field of research and innovation. As we stand on the precipice of a technological revolution, we witness the unfolding of quantum algorithms designed to tackle real-world problems. Researchers are developing quantum annealers, which utilize quantum superposition and entanglement to optimize complex systems, from logistics to financial modeling. The marriage of these principles with artificial intelligence may one day allow us to unlock solutions hidden within vast data sets, revolutionizing industries and enhancing our understanding of complex phenomena. In this exploration, it is essential to acknowledge the challenges and nuances that accompany these advancements. The field of quantum computing is still in its infancy, with obstacles such as error correction and qubit coherence times posing significant hurdles. Yet, the relentless pursuit of knowledge drives scientists and engineers to innovate, unraveling the mysteries of quantum mechanics and pushing the boundaries of what is possible. As we contemplate the implications of superposition and entanglement, we might wonder how these principles will shape our future. With each discovery, we inch closer to a profound understanding of the universe and our place within it. The exploration of quantum mechanics invites us to embrace a reality that is as complex as it is beautiful, encouraging us to remain curious and open to the wonders that lie ahead. Imagine the day when quantum technologies become integral to our lives, fundamentally altering our approach to computation, communication, and even our understanding of consciousness. The journey through quantum mechanics continues to unfold, revealing a landscape rich with potential, where the interplay of superposition and entanglement invites us to dream of a future unbounded by the constraints of our current understanding. Each step forward not only deepens our knowledge, but also inspires awe, a reminder of the intricate dance of particles that compose the very fabric of our reality. Chapter 8. Measurement and the role of wave functions. In the mesmerizing landscape of quantum mechanics, the act of measurement introduces a profound complexity known as the measurement problem. This issue arises from the fundamental question of how and why the act of measuring a quantum system leads to a definite outcome, seemingly collapsing the myriad possibilities described by its wave function into a singular reality. It is as if we stand at the edge of a vast chasm, peering into a world where potential exists in abundance, yet a single choice transforms the landscape into a concrete experience. Consider a particle that exists in a superposition of states, embodying multiple possibilities at once. When we measure this particle, we force it into a specific state, effectively selecting one outcome from a spectrum of potential realities. This transition from potential to actuality raises questions about the nature of reality itself. Does the wave function represent a real physical state? Or is it merely a tool for predicting the results of measurements? This uncertainty is at the heart of the measurement problem, leading to various interpretations that seek to illuminate the shadows of quantum mechanics. One prominent interpretation is the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. This perspective posits that the wave function encapsulates all possible states of a system until an observation occurs, at which point it collapses into a single state. Imagine a curtain drawn across a stage, obscuring the performance until the moment the curtain rises, revealing the actors in a singular scene. Yet this interpretation invites skepticism, as it does not fully address the underlying reality of the wave function itself. In contrast, the many worlds interpretation, proposed by Hugh Everett III, offers a radically different perspective. According to this view, all possible outcomes of a quantum measurement actually occur, but in separate non-communicating branches of the universe. Picture an expansive forest, with each path representing a different outcome of a decision made at a crossroads. As we venture down one path, the others diverge, each leading to its own unique reality. This interpretation shifts the burden of understanding the measurement problem, suggesting that rather than collapsing into a single state, every possibility unfolds in its own realm. Another fascinating approach to the measurement problem is found in the de Broglie-Bohm theory, also known as pilot wave theory. This interpretation introduces a deterministic framework, where particles are guided by a wave function, maintaining a hidden variable that dictates their behavior. Imagine a boat sailing across a lake, guided not by the whims of the wind, but by a predetermined course. This view reintegrates a sense of determinism into the quantum realm, challenging the probabilistic essence that characterizes other interpretations. As we ponder these interpretations, we may ask ourselves, how does the act of measurement influence the wave function itself? When we engage in the process of measuring, we not only extract information, but also alter the very state of the quantum system. This interaction underscores the profound interconnectedness between observer and observed, a theme that resonates throughout quantum mechanics. Experimental setups provide illuminating insights into the measurement problem and the effects of measurement on wave functions. One such experiment is the double-slit experiment, which showcases the duality of wave-particle behavior. When particles, such as electrons, are sent through two slits, they create an interference pattern on a detection screen, suggesting wave-like behavior. However, when we measure which slit the particle passes through, the interference pattern disappears, revealing the particle-like nature of the electron. This phenomenon invites us to ponder: what happens to the wave function during the act of measurement? Imagine the particles as tiny phantoms, gracefully weaving through the slits, creating a beautiful pattern of undulations. Yet, the moment we attempt to discern their path, the dance is disrupted, and they collapse into distinct particles. The act of measurement, then, not only reveals information, but also transforms the underlying reality of the quantum system. Another compelling experiment is the quantum eraser, which intricately weaves together the themes of measurement and information. In this setup, entangled particles are produced, with one particle sent through a double-slit apparatus, while the other is directed toward a detector. Initially, when no information is available about which path the particle took, interference patterns emerge. However, if we later obtain which path information, the interference pattern vanishes. Remarkably, if we erase the which path information after the fact, the interference pattern returns, suggesting that the active measurement can indeed retroactively affect the wave function. This experiment invites us to reflect on the nature of reality itself. Does the past change depending on our present actions? In the quantum realm, the interplay between measurement and wave functions reveals a complexity that challenges our classical intuitions. Moreover, advancements in technology have allowed scientists to explore the nuances of measurement and wave functions with unprecedented precision. Quantum technologies, such as quantum computing and quantum cryptography, leverage the peculiarities of quantum mechanics to redefine our understanding of information and computation. These innovations are nurtured by the principles of superposition and entanglement, illuminating the potential for new ways to process and transmit information. As we explore the implications of measurement in quantum mechanics, it becomes evident that this realm is not merely a playground of abstract concepts, but a domain where our understanding of reality is continuously reshaped. The interactions between the observer and the observed, the delicate balance between potential and actual outcomes, and the philosophical questions that arise from these interactions beckon us to reconsider the very nature of existence. What if our understanding of measurement is merely a reflection of our limitations as observers? What if the act of measurement is intertwined with the fabric of reality, shaping it in ways that elude our comprehension? As we stand at the threshold of quantum mechanics, we find ourselves not only as learners but as active participants in a grand narrative that unfolds in the universe. The enigmatic role of wave functions in this narrative invites us to contemplate the possibilities that lie ahead. Each measurement creates ripples in the fabric of reality, shaping the wave functions of particles and, in turn, influencing the outcomes of future measurements. The continuous interplay between measurement, wave functions, and interpretations beckons us to explore the depths of our understanding, encouraging us to venture beyond the surface of known truths. As we proceed on this journey through the quantum landscape, we remain anchored by the knowledge that each question leads to new horizons of inquiry. The act of measurement, the transformations of wave functions, and the interpretations that arise from these phenomena intertwine to create a rich tapestry of understanding. In this realm, the familiar laws of classical physics dissolve, leaving behind a world that is vibrant, complex, and full of possibilities waiting to be explored. The measurement problem delves deeply into the heart of quantum mechanics, revealing the intricate relationship between observation and reality. When we measure a quantum system, we not only extract information but also fundamentally alter the state of that system. This interaction raises profound questions about the nature of reality. Are we merely observers, or do our actions actively shape the universe around us? Consider the implications of measurement further. When a wave function collapses, what exactly is lost? The multitude of possibilities represented by the wave function transforms into a singular outcome, as if a painter had mixed all colors on a palette and, with a single stroke, created a solitary image. This brings to mind the words of physicist John von Neumann, who suggested that the act of measurement is not merely a passive observation but an active engagement that irrevocably transforms the quantum state. The nature of this transformation invites us to explore various interpretations that attempt to reconcile the measurement problem with our understanding of reality. Each interpretation offers a different lens through which we can view the act of measurement and its consequences. For instance, the objective collapse theories propose that wave functions collapse spontaneously, independent of observation, suggesting that reality possesses an inherent randomness. This perspective challenges our intuitive grasp of causality and determinism, inviting us to ponder, is our understanding of reality not as fixed as we once believed? As we venture into experimental setups that illustrate the nuances of measurement effects, the thought experiments become increasingly revealing. The delayed choice experiment, for instance, offers a stunning insight into the behavior of quantum systems. In this setup, the decision to measure a particle's path can be made even after the particle has passed through the double slits. This suggests that the act of measurement can retroactively influence the behavior of particles, as if time itself is intertwined with the fabric of quantum mechanics. Imagine standing at a crossroads, where your choice at a later moment determines the path you've already taken. What does this say about the flow of time and causality in our universe? Entanglement further complicates our understanding of measurement. When two particles become entangled, the measurement of one instantaneously affects the state of the other, regardless of the distance separating them. This phenomenon challenges our classical notions of locality and suggests that information can be shared across vast distances in a manner that transcends our familiar experiences. Albert Einstein famously referred to this as spooky action at a distance, highlighting the strangeness of entangled particles that seem to communicate instantaneously. How does this instantaneous connection fit into our understanding of space and time? To illustrate these principles, consider the aspect of quantum communication. Quantum key distribution, an application of entanglement, allows two parties to securely share information by leveraging the peculiarities of quantum mechanics. The security of this method hinges upon the fundamental nature of measurement. Any attempt to eavesdrop on the communication alters the state of the particles involved, alerting the parties to the presence of a third party. This intertwining of measurement and security exemplifies how deeply the act of observing affects the very fabric of the system. The experiments that probe the measurement problem not only deepen our understanding of quantum mechanics, but also serve as a bridge between the abstract and the tangible. As we analyze these setups, we uncover the delicate threads that connect measurement, wave functions, and the interpretation of reality. Each experiment acts as a window into the quantum realm, allowing us to witness the profound implications of our observations. As we reflect on these concepts, we might ask ourselves, what does it mean to know something in the quantum world? Is knowledge simply about obtaining information, or does it involve a more profound transformation of reality? The act of measurement, then, becomes a dance of uncertainty, a reminder of the fluid boundaries that define our understanding of existence. Moreover, the philosophical implications of the measurement problem extend beyond the confines of physics. They beckon us to confront our perceptions of reality, knowledge, and existence itself. As we grapple with these ideas, we might find ourselves contemplating the nature of consciousness and its role in shaping our understanding of the universe. Are we mere spectators in a grand play, or do we hold a more active role in the unfolding narrative of reality? In the journey through the quantum landscape, the interplay between measurements and wave functions continues to inspire curiosity and wonder. Each question leads us deeper into the mysteries of the universe, urging us to explore the intricacies of existence. As we stand on the precipice of understanding, we embrace the profound complexity of the quantum world, where nothing is as straightforward as it seems, and where every measurement resonates with the echoes of untold possibilities. As we tread further into this mesmerizing domain, we are reminded that the act of measurement is not merely a mechanical process, but a profound interaction that shapes the very essence of reality. This understanding compels us to pause and reflect on the nature of our own inquiries, the questions we ask, and the answers we seek. The quantum realm beckons us to explore the profound depths of what it means to observe, to know, and to exist in a universe that is ever evolving, rich with potential, and filled with the promise of discovery. Chapter 9. Complex Systems and Wave Function Interactions. In the intricate realm of quantum mechanics, the behavior of particles becomes a symphony of interactions, particularly when we turn our attention to wave functions in many body systems. Imagine a bustling marketplace, where various individuals move, converse, and interact, each influencing the other in a complex web of relationships. Similarly, in many body quantum systems, the wave functions of individual particles intertwine, creating a rich tapestry of collective behavior. Wave functions in many body systems become intricate because they must account for each particle's state while also representing the correlations between them. When particles are indistinguishable, as is often the case in quantum systems, the wave function must adhere to specific symmetry principles. For fermions, particles that obey the Pauli exclusion principle, the wave function must change sign when two particles are exchanged. This property leads to the emergence of phenomena such as electron degeneracy, where particles are compelled to occupy different quantum states. Conversely, for bosons, which can occupy the same state, the wave function remains unchanged upon exchange, allowing for intriguing behaviors like Bose-Einstein condensation. Imagine a cold, dense cloud of bosons, where they coalesce into a single quantum state, behaving as though they are a unified entity. This collective behavior is a striking illustration of how wave functions in many body systems can transcend the individual, leading to emergent properties that are not present in isolated particles. As we explore these interactions, we uncover the delicate balance between individual quantum states and their collective manifestations. Central to the understanding of these many-body systems is the concept of quantum fields. At its core, a quantum field is a fundamental entity that permeates space, with particles being excitations or disturbances within this field. Picture a calm lake where a stone is dropped, creating ripples that spread outward. These ripples represent the excitation of the field, and just as the stone's impact creates a cascade of interactions, so too do interactions within quantum fields result in wave functions that describe the behavior of particles. Quantum field theory provides a framework through which we can comprehend the connections between wave functions and particle interactions. It posits that particles are not simply isolated points, but rather manifestations of underlying fields that interact with one another. The rich interplay of these interactions leads to a variety of phenomena, including the creation and annihilation of particles, revealing a dynamic world that is ever-evolving. Wave function interactions in quantum statistical mechanics further illuminate our understanding of complex systems. Quantum statistical mechanics extends the principles of statistical mechanics into the quantum realm, allowing us to describe systems with many particles where quantum effects are significant. In this context, the role of wave functions becomes paramount, as they dictate the statistical behavior of particles. Imagine a grand orchestra where each musician plays a distinct instrument, yet together they create a harmonious sound. The wave functions of particles in a quantum statistical system can be thought of as the individual notes played by each musician. The collective outcome is influenced by the probabilistic nature of these wave functions, resulting in behaviors that can be predicted by statistical distributions. One remarkable example of collective behavior in quantum systems is the phenomenon of superconductivity. When certain materials are cooled below a critical temperature, they exhibit the remarkable ability to conduct electricity without resistance. This occurs when electrons form Cooper pairs, a collective state, where they move through the lattice of the material in a coordinated manner. The wave function describing this state encompasses the interactions between pairs of electrons, allowing them to behave as a single entity, thus enabling the material to conduct electricity with perfect efficiency. Another intriguing manifestation of collective behavior is found in quantum phase transitions. These transitions occur when a system undergoes a fundamental change in its ground state due to variations in external parameters, such as temperature or pressure. Picture a group of people in a room, initially scattered, who suddenly align in a singular direction upon the signal of a conductor. This alignment can be likened to the transition of a quantum system from one phase to another, driven by the underlying wave function interactions that dictate the system's behavior. As we explore these examples, we find that the collective behaviors arising from wave functions are not just theoretical constructs. They have real-world implications. Superconductivity, for instance, holds promise for revolutionizing electrical systems, while understanding quantum phase transitions can lead to advances in materials science and quantum computing. Moreover, the field of quantum computing itself relies heavily on the principles of wave functions and their interactions. Quantum bits, or qubits, are the building blocks of quantum computers, and their ability to exist in superposition enables quantum algorithms to process information in ways that classical systems cannot. The interplay of wave functions allows qubits to interact and entangle, creating a complex network of information that can be harnessed to solve problems of unprecedented complexity. As we journey through the intricate landscape of complex systems and wave function interactions, we are reminded of the profound interconnectedness of the universe. Each particle, each wave function, contributes to a greater whole, echoing the sentiments of physicist Albert Einstein, who once reflected on the beauty of the cosmos, emphasizing how everything is related. In this interconnected tapestry, we find ourselves not merely as observers, but participants in a grand quantum narrative. The stories of many-body systems, quantum fields, and wave function interactions reveal the underlying principles that govern our reality. They invite us to ponder the possibilities that arise when individual entities come together, creating a rich and dynamic interplay that defines the very nature of existence. As we continue to explore the depths of these concepts, let us remain open to the wonders of the quantum world, where the boundaries of our understanding stretch ever farther, revealing new insights and potentialities. Each discovery beckons us to consider the implications of wave functions and their interactions, and how they shape not only the microscopic world of particles, but also the macroscopic universe we inhabit. The journey through complex systems, like the melodic notes of a symphony, offers a calming yet exhilarating exploration of the fundamental nature of reality. As we deepen our exploration of wave functions in many body systems, we encounter an extraordinary phenomenon: the interactions that arise from quantum fields. In this framework, the very essence of particles is revealed not as isolated entities, but as manifestations of underlying fields that vibrate and resonate through the universe. Each particle, like a note in a symphony, contributes to the overall harmony, while simultaneously being influenced by the vibrations of its neighbors. Consider the concept of quantum field theory, which elegantly describes how particles are generated and annihilated through interactions with these fields. Imagine a field as an ocean that ebbs and flows, where particles are like waves that rise and fall, appearing and disappearing in a continuous cycle of creation. The interactions between these waves lead to a dynamic landscape filled with possibilities, where new particles can emerge from the energy of the field itself, much like how a wave can suddenly rise and crash upon the shore. The role of wave functions becomes increasingly critical in this context. In quantum statistical mechanics, the wave functions of particles govern the statistical behavior of systems with many interacting components. Picture a bustling city, where each individual represents a particle, their myriad interactions shaping the environment around them. The aggregate behavior of all these individuals, rushing, pausing, and interacting, can be described statistically, just as wave functions dictate the collective behavior of particles in a quantum system. One of the fascinating aspects of wave functions in quantum statistical mechanics is their ability to encapsulate the complexities of collective phenomena. This is particularly evident in systems where particles exhibit similar properties, such as in a gas of indistinguishable particles. In such systems, the wave functions can be combined to reflect the overall probability distribution, creating a robust framework for predicting the behavior of the ensemble. Imagine a peaceful lake at dawn, where the surface is initially smooth and undisturbed. As the sun rises, gentle ripples begin to form, each one a reflection of an interaction occurring beneath the surface. These ripples are akin to the statistical behaviors of particles whose wave functions are now intertwined. The collective disturbance of the water reveals the underlying currents of interaction, much like how the collective behavior of particles demonstrates the profound effects of their wave functions. An exemplary manifestation of this collective behavior is found in the phenomenon of superfluidity. When certain liquids are cooled to temperatures near absolute zero, they can flow without viscosity, allowing them to move through narrow channels without losing energy. This extraordinary state arises from the coherent wave functions of the particles that compose the liquid, which behave collectively as a unified entity. Imagine a serene river flowing smoothly, unimpeded by obstacles. illustrating how the wave functions of the particles in a superfluid state coalesce into a single, flowing wave. The insights gained from studying wave functions in many body systems also extend to quantum phase transitions, where the ground state of a system changes fundamentally due to external influences. Picture a group of dancers performing in unison, initially scattered across the stage. With a single cue, they transform their arrangement, aligning in a synchronized formation. This transformation mirrors how a quantum system can shift between phases, driven by the correlations established through wave function interactions. As the temperature of a material is altered, its particles may undergo a phase transition, transitioning from a disordered state to an ordered one, akin to the dancers finding their rhythm. These transitions do not merely signify a change in physical properties. They represent a profound alteration in the underlying wave functions that define the state of the system. In the realm of quantum systems, we also encounter the phenomenon of collective excitations, where wave functions interact to produce new states that exhibit unique properties. These excitations arise in systems such as solids, where the interactions between atoms can lead to vibrational modes known as phonons. Imagine a tightly woven fabric, where the threads interact and vibrate together, creating patterns of movement that extend throughout the material. This collective behavior results in properties such as thermal conductivity and sound propagation, illustrating how wave functions can dictate the macroscopic characteristics of materials. The rich tapestry of quantum phenomena continues to unfold as we explore the implications of wave functions in various systems. Just as the principles of wave functions govern the microscopic world, their influence permeates into the macroscopic realm, shaping the materials and technologies that form the foundation of our reality. As we contemplate the impact of wave functions on complex systems, we are drawn to the realization that understanding these interactions is not merely an academic pursuit. The insights gained from quantum mechanics have profound implications for fields as diverse as material science, medicine, and information technology. The ability to manipulate wave functions and their interactions opens doors to advancements in quantum computing, where the intricate dance of qubits could revolutionize our approach to problem solving. In this ever-expanding landscape of quantum mechanics, we are offered a glimpse into the interconnectedness of all things. Each wave function, each particle, contributes to the grand narrative of the universe, echoing the thoughts of physicist Richard Feynman, who once remarked on the beauty of nature's complexities. The journey through complex systems and wave function interactions invites us to reflect on the wonders of the quantum realm. Each discovery unveils new perspectives, urging us to remain curious and open to the mysteries that lie ahead. As we continue our exploration, we find ourselves not only witnesses to the unfolding story of the universe, but also participants, intricately woven into the fabric of existence itself. Chapter 10: Future Directions in Quantum Mechanics Research. As we look toward the horizon of quantum mechanics, we find ourselves at the intriguing crossroads of emerging theories and interpretations surrounding wave functions. The landscape is rich with possibilities as scientists explore the very essence of what wave functions represent. These theories challenge the traditional view, suggesting that wave functions may not merely signify probabilities, but could embody deeper connections to the underlying reality of the universe. Imagine a world where wave functions are not static entities, but rather dynamic participants in the unfolding narrative of quantum interactions. The many worlds interpretation, championed by Hugh Everett, posits that every quantum event spawns a multitude of parallel realities, each governed by its own wave function. Picture a branching tree, where each decision creates a new pathway, leading to a cascade of alternate outcomes. This perspective invites us to reconsider the nature of existence itself. What if every choice and every measurement splits the universe into countless versions of reality? Moreover, the pilot wave theory, formulated by Louis de Broglie and later expanded by David Bohm, introduces the idea of a guiding wave that influences particle behavior. This theory suggests that particles have definite positions and velocities, yet they are steered by a wave function that embodies the potentiality of their paths. Imagine a river, flowing with an unseen current that directs the course of every droplet. This notion challenges the probabilistic interpretations by reintroducing determinism, leading us to ponder, does the universe operate on a hidden level of certainty, masked by our perceptions of randomness? The exploration of these interpretations not only deepens our understanding of quantum mechanics, but also fuels the development of quantum technologies. Quantum computing, a revolutionary advancement, harnesses the principles of superposition and entanglement to perform calculations far beyond the scope of classical computers. Imagine a vast library where each book contains not just one story, but a multitude of narratives, all simultaneously accessible. Quantum computers, operating on qubits instead of traditional bits, can explore this library of possibilities at an unprecedented pace, opening doors to solving complex problems in cryptography, materials, science, and drug discovery. In the realm of quantum cryptography, the promise is equally tantalizing. The principles of quantum mechanics ensure that any attempt to eavesdrop on a quantum communication will disturb the system, alerting the parties involved. Picture a secure conversation taking place in a garden surrounded by an invisible barrier. Any intruder would trigger a reaction, safeguarding the sanctity of the exchange. This breakthrough in secure communication could redefine how we share sensitive information, fortifying our digital interactions against the threats of hacking and surveillance. Quantum sensing, too, is poised to revolutionize fields such as navigation, medical imaging, and environmental monitoring. Utilizing the delicate properties of quantum states, quantum sensors can achieve unprecedented sensitivity, revealing details that classical instruments might miss. Imagine a butterfly flapping its wings, sending ripples through the air. A quantum sensor can detect those subtle changes, offering insights into our world that were once thought to be unattainable. Such advancements have the potential to enhance our understanding of the universe, providing tools to explore everything from the depths of the ocean to the farthest reaches of space. Yet, alongside these exciting developments lie open questions and challenges that continue to perplex researchers. How do we reconcile the various interpretations of wave functions? What does it mean for our understanding of reality when we consider the implications of many worlds or hidden variables? Each approach offers a unique lens through which to view the cosmos, yet none provides a definitive answer. This ambiguity begs us to confront the limitations of our current knowledge and to embrace the uncertainty that lies at the heart of quantum mechanics. Furthermore, the challenge of scaling quantum technologies remains. Creating stable and error-resistant qubits is akin to capturing fireflies in a jar. The delicate nature of quantum states makes them susceptible to environmental disturbances and decoherence. Researchers are tirelessly working to overcome these obstacles, developing error correction methods and exploring new materials to create robust quantum systems. Imagine the intricate choreography of a ballet, where every dancer must harmonize perfectly to create a seamless performance. Achieving this balance in quantum systems is crucial for the future of quantum computing and sensing. As we contemplate the potential impact of wave functions on future science, we begin to see their implications stretch far beyond the confines of the quantum realm. The very nature of wave functions invites us to reconsider fundamental concepts such as causality, determinism, and the fabric of reality itself. How might an enhanced understanding of wave functions influence fields like cosmology or biology? Could they reshape our approach to understanding consciousness or the origins of the universe? The journey ahead is one filled with promise and possibility. As physicists and researchers continue to unravel the mysteries of quantum mechanics, the exploration of wave functions will undoubtedly play a pivotal role in shaping the future of science. Each discovery, each new interpretation adds another layer to our understanding of the universe, illuminating the intricate connections that bind us to the cosmos. We are on the brink of a new era, where the insights gained from quantum mechanics could redefine our technological landscape and deepen our comprehension of reality. Picture a dawn breaking over a vast expanse, casting light on new horizons, inviting us to explore further into the depths of existence. The potential of wave functions, as we continue to explore their nature, holds the key to unlocking mysteries that may have once seemed impenetrable. As we stand at this threshold, let us embrace the curiosity that drives our quest for knowledge. With every question asked and every theory proposed, we edge closer to revealing the elegance of the quantum universe, where wave functions serve not only as mathematical abstractions, but as profound reflections of the cosmos itself. As we journey deeper into the future of quantum mechanics, we uncover the emerging theories and interpretations of wave functions that continue to captivate the imaginations of physicists. These evolving perspectives challenge the conventional paradigms, suggesting that the wave function may serve as a gateway to understanding not just the quantum world, but also the very nature of reality itself. One of the most thought-provoking theories posits that wave functions could reflect more than mere probabilities. They may represent an inherent interconnectedness that underlies all existence. Imagine a vast web, with each strand representing a particle's wave function, intricately woven together to form a cohesive whole. This interconnectedness could imply that every measurement influences the entire fabric of the universe, resonating through the cosmos in ways we are only beginning to comprehend. The potential of quantum technologies, particularly in computing, cryptography, and sensing, offers a glimpse into a future where these theories might be applied. Quantum computing, for instance, stands at the forefront of this technological revolution. Unlike classical computers, which process information in binary, quantum computers utilize qubits that can exist in multiple states simultaneously due to superposition. Picture a vast library where each book can be read in parallel, allowing for solutions to complex problems at a speed unimaginable with today's technology. The implications of such advancements are staggering, with the potential to tackle challenges from optimization problems to simulations of molecular interactions in drug discovery. In the realm of quantum cryptography, the principles of quantum mechanics promise a level of security previously deemed unattainable. Quantum key distribution allows two parties to share a secret key with the assurance that any attempt at eavesdropping would inevitably alter the communication. Imagine a secure conversation shielded by an impenetrable force field, where any intrusion would be immediately noticeable, ensuring the privacy of the exchange. Quantum sensing, another exciting frontier, leverages the unique properties of quantum states to achieve extraordinary sensitivity. These sensors can detect minute changes in physical phenomena, leading to advancements in fields such as medicine and environmental science. Envision a scenario where medical imaging captures the faintest signals from the body, revealing insights into health conditions that were once elusive. Such advancements could revolutionize diagnostics, enhancing our understanding of diseases and improving patient outcomes. Yet, as we explore these tantalizing prospects, we are met with a series of open questions and challenges that loom large in the field of quantum mechanics. How do we reconcile the myriad interpretations of wave functions, each offering a different perspective on the nature of reality? The many worlds interpretation suggests an infinite number of parallel universes, while the pilot wave theory hints at a deterministic framework beneath the probabilistic surface. This diversity of thought invites us to consider, are we on the brink of a unified theory that can encompass these varying viewpoints, or are we destined to navigate a landscape of competing paradigms? The pursuit of a comprehensive understanding of quantum mechanics also faces practical hurdles in the realm of technology. As researchers work tirelessly to create stable qubits for practical use, they encounter the challenge of decoherence, where environmental influences disrupt the delicate quantum states. Imagine a finely tuned musical instrument, its harmony disrupted by external noise. Achieving the balance required to maintain coherent quantum states is fundamental to realizing the full potential of quantum technologies. The exploration of wave functions is not confined to the realm of quantum physics alone. As our understanding deepens, we begin to see the potential impact of these concepts on broader scientific disciplines. Could the principles that govern quantum mechanics ultimately inform our understanding of complex systems in biology? What if the probabilistic nature of wave functions could shed light on the intricate behaviors of ecosystems or the dynamics of neural networks in the brain? The interconnections between these fields offer fertile ground for interdisciplinary research, fostering collaborations that may lead to groundbreaking discoveries. The implications of wave functions stretch into the cosmos itself. As we contemplate the nature of reality, we find ourselves asking how these quantum principles might influence our understanding of the universe's origins. Could wave functions offer insights into the behavior of dark matter or the fabric of spacetime? Physicist Niels Bohr once remarked, "Everything we call real is made of things that cannot be regarded as real." This perspective invites us to reflect on the very foundations of our understanding, and to embrace the mysteries that lie at the intersection of quantum mechanics and cosmology. As we stand at the precipice of new discoveries, we are reminded of the words of physicist Richard Feynman, "The imagination of nature is far greater than the imagination of man." This sentiment resonates deeply as we consider the future of quantum mechanics and its potential to illuminate the profound connections that bind us to the universe. Each new interpretation, each technological advancement, invites us to explore the unseen realms of existence, urging us to question our assumptions and expand the horizons of our understanding. The journey through the landscape of quantum mechanics is not merely an academic pursuit. It is a quest that beckons us to explore the very essence of reality. As we delve into the future directions of research, we are invited to embrace the unknown with open hearts and curious minds. The path